Here we go. Okay, so guys, today what we're doing is we are starting a segmented, for lack of a better term, wait, no, we don't need to do that anymore. Let me start over. So this is what I used to do, but I'm realizing I don't have to do it this way anymore. So guys, we have 3 more things to cover in this unit. We need to cover strong titrations. We need to cover KSP, which is the breaking down of slightly soluble salts. And we need to cover weak titrations, not titrating buffers, but titrating weak acids and bases. So with that in mind, here I can just scratch this up on the, okay, this is cool. So we need to do strong, we need to do KSP, and we need to do weak titrations. Now here's the trick. This is very complicated. This is really straightforward, and this is fairly straightforward. So what I've done in years past to try to maximize our time is I've taught these two together today. We would do strong titrations, and then we would do KSP calculations all in the same day. And then this would be a second day leading up to the test. Here's what happened. In 2014, when they rewrote the AP test, they have made this a larger component of the test. And so what I did in response is I broke these apart and no longer glossed over KSP. But what I've done for years, well, for those years, has been I would go one day here, a second day here, and a third day here. And it would get weird because it would go strong titrations, then salts, then weak titrations. Because this just came to me. I know it's so obvious, right? I think what we're going to do this year is reorder them. So today we will do strong titrations, then either Thursday or next Monday, the following Monday, we'll do weak titrations, and then we'll wrap up the unit with KSP, thereby keeping the titrations together. That works better. The only thing I think that may screw up, though, is the homework, because I think that this homework assignment includes some KSP problems. So let's talk when we go over homework. Because guys, as a matter of fact, like if you check this out, look at the heading of the notes. Notice what it says. It says still strong titrations in KSP. I didn't even change, I changed the title slide, but I forgot to even change that. So when we get to the end of today, let's spend a second, look at the problems and see if the KSP problems are in there. So, all right, so more than you needed to know, but you'll find that helpful. All right, so guys, here we go. So don't be judicious in terms of the notes you take. I want to sort of set the stage. So guys, this is where we're at and this is where we're going. So the fundamentals are this, and you don't need to write this down. Guys, what you're going to find out is there are 4 fundamental types of titrations that we could be studying. One of them is what we call strong titrations. Strong acid, strong base, strong acid. Those we're going to do today. Another type are what we call weak titrations. That is either a weak acid with a strong base or a strong base with a weak acid. That we're going to do, I think, next time. Then guys, another type of titration that we can do are what are called polyprotic acid titrations. The idea being that we have an acid that can give away more than one hydrogen. Then guys, the third type of titration that we can do are weak titrations, where you put a weak acid into a weak base or a weak base into a weak acid. Now guys, here's the beautiful thing. We don't have to do either one of these last two. We do not have to study polyprotic acid titrations. We also don't have to study weak titrations. So all we've got to do are these, realizing that we've already done a different type of titration, right? The buffer titrations. So really this should be in addition to the buffer titrations. All that we have to do, guys, is, oh, that works. That didn't work. All that we have to do is these two. So we've got to do strong, and weak, strong, and we're good. Okay? All right. So guys, with that said then, If you need to include these thoughts in your notes, good heavens. If you need to include these thoughts in your notes, feel free. If not, I think we're okay. You decide. So guys, we need to sort of define some terms. So when we talk about titration, are we all okay with the idea that what we're talking about is adding a solution with known concentration to a solution that we don't know the concentration of? Are we okay with that? Is that okay? So guys, as we talk about that then, what you're going to find is that we can either track the pH of these things qualitatively or quantitatively. So guys, when we do qualitative titrations, how do we know when the titration's over? What do we use? An indicator. It turns, and you guys understand that they don't always turn pink. It's just that we always have been using the same indicator. But guys, when we do qualitative titrations, we are just looking for an indicator to change color. You're going to find out, and forgive me guys, Rachel and Valeria, in lab, the next titration we're going to do with the pH meter, we're going to do it more quantitatively. So, with that said, let's now talk about indicators. And this is where you need to start taking notes. So guys, when we talk about indicators, we're talking about things like phenolphthalein. These solutions that we add to acid-base titrations that change color. And guys, up until now, you've been functioning under the misconception that the phenolphthalein turns colors, turns pink at pH 7. That's actually not true. Phenolphthalein does not change color at pH 7. I'll show you what it does in a minute. But guys, understand, indicators like phenolphthalein do not have to indicate exactly the pH that you're looking for. And I'll show you what that means in a minute. So what do indicators actually do? Well, guys, the trick is indicators indicate what we call the equivalence point. You'll notice I've underlined it. Now let's define it. So guys, the equivalence point is the point at which we've added stoichiometrically equal amounts of titrant to the thing we're titrating. Typically, that's a base into an acid or an acid into a base. But guys, the bottom line is when we reach that equivalence point, the key is the word equal. It's the point where we have added equal amounts of acid and base. You okay with the idea? And I'll show you more about this in a minute. I'll show you what equivalence point means in a second. Now guys, getting back to this idea of indicators, and I'll show you more about this in a minute as well, it's going to be helpful for you to understand that most indicators are actually weak acids. And I'll show you more about that in the next slide. But guys, now that you've sort of got this background ideas, what is titration? What role do indicators play? What are indicators? Weak acids. Guys, what we're about to do, this is the way the rest of the day is going to play out. We're first of all going to talk really quickly about how indicators work. The AP curriculum expects you to understand at some level the way these things function. Then what we're going to do is we're going to spend the rest of the day today talking about titration curves. And guys, you want to scratch this down in your notes. So guys, titration curves are simply graphs that represent the amount of titrant that you've added versus pH. And what you're going to find out as we get into these titration curves is that we can break them down into 4 regions, and we're going to talk about them that way. So now we sort of understand our marching orders for today. Guys, the first thing we're going to do is we are going to very briefly explain to you the way things like phenolphthalein work. Then, once we understand that, we're going to start studying titration curves. We're going to look at the 4 regions of a titration curve and use that to allow us to talk about things like equivalence point. Then, guys, when we're done with that conversation, we are going to mathematically study strong titrations, and that'll be our day. You guys ready to go? Okay, so guys, first of all, indicators. So the indicator that you've used in this class or during lab last year or whenever has been this stuff. Don't try to write any of this down. Guys, this is phenolphthalein. That is what a phenolphthalein molecule looks like. Now, first of all, when you're given a dropper of phenolphthalein in lab, what is the phenolphthalein dissolved in? Because this is a solid. So maybe we should talk about this first. Weak acid or weak base? How do you know it's a weak acid? What are you looking at? So guys, you've got a carbon bonded to an oxygen, bonded to the hydrogen. And guys, this hydrogen is actually acidic. That those hydrogens, and actually only one of them, those hydrogens, one or the other, are actually acidic and can be removed. So this is a weak acid. But because it's a weak acid, when it's not dissolved, what phase will it be in? Do you remember? It's going to be a solid. So guys, this is maybe important for you to know. When I take phenolphthalein powder and turn it into the stuff that I put in those dropper bottles, have any of you smelled it? What's the phenolphthalein dissolved in? It's not water. It's not, no, it's actually, that would be bad because then you'd have another weak acid. It's not, it's actually an alcohol. Yeah, guys, all of these indicators are dissolved in alcohol. So why dissolve them in alcohol? Well, alcohol is neither an acid nor a base. It is something that can dissolve, remember, hydrogen bonding. It can form hydrogen bonds with phenolphthalein and get it to dissolve, but it's not an acid or a base. So we dissolve these in alcohols. But guys, here's the thing you need to know about phenolphthalein. When it breaks apart into this. It's a weak acid. So what happens is one of these hydrogens is released, and when that hydrogen is released, there's our proton, and this is a weak acid just like any other weak acid. Go ahead, Thomas. Exactly. Yeah, right. So, oh man. You know what? I don't want to fight this continually. Let me just shut this down and restart it and see if I can get it to behave better. Okay, so right there, right here, right, let's just try this. I don't know, my recording's completely different. Okay, so I think I'm good there. So let me repeat to everybody what you're saying. Guys, remember we talked about this idea that for this to be an organic acid, there needs to be that double bond that's created there with another oxygen, and that causes drift, which causes polarity, which causes this to be acidic. And typically that's the case. But it turns out that in more complicated organic molecules, and we're not going to go into why, but in more complicated organic molecules like this, you can actually have enough drift. You can have enough drift being created just by the rest of this mass that it actually will polarize that bond enough to cause it to weaken and break. But, and I frankly don't know the number, it would be interesting to know the Ka value for phenolphthalein. It's going to be itty bitty small. They're not very strong weak acids. But again, you're right that typically we would expect this, but in these big macro molecules, it's not always necessary. Yeah. No. Oh, wait, this? Yeah, and this is something that you will never have to do in this class. These are what are called stereo diagrams. And so when you draw stereo diagrams, you understand carbon likes to be tetrahedral. And so the way that you draw this is you draw it so that two of the bonds are in the plane of the axis, and then one of them you draw with a triangle, which is to represent coming out of the board, and then the other one you draw receding into the board, and you can actually draw these things trying to represent them three-dimensionally, which is yet another thing that makes organic chemistry ridiculous.
So is any of that drift coming from the location, like the three-dimensional
Mm-hmm.
OH groups and be closer to another one?
Definitely could be. Absolutely. Yeah, that certainly could be the case. So, guys, with all of that said, this is the magic. This is what makes this molecule function as an indicator, because it turns out that phenolphthalein in its acidic form is colorless, and in its protonated form it turns pink. So this ion is pink in water, and this, the unprotonated form, is colorless in water. So how does that then allow this stuff to function? Well, guys, when does phenolphthalein turn pink? Is it pink in the presence of a base or the presence of an acid? Think about it, guys. Think about the titrations that we've done. You've got a bucket of vinegar or Sprite or whatever else, and remember, you've got this, and you've got the stirrer plate. And so, guys, when you put the phenolphthalein in the vinegar, does it turn pink? No, it's colorless, right? So phenolphthalein is colorless in an acid, and it turns pink as you add a base. Well, why would that be true? So if you think about it, when you put it in an acid, there's a lot of this, right? And if there's a lot of that, what does Le Chatelier's principle say is going to happen to the equilibrium? It's going to go to the left, and the equilibrium is pushed to the colorless side. Then, as you add base to this, the base ties up these protons as water. The hydrogen ion concentration drops. That shifts the equilibrium to the right, and eventually you end up with a predominance of this stuff, and the solution turns pink. So guys, that's how indicators work. You don't have to get into a lot of the nitty-gritty details. You just need to understand that indicators tend to be weak acids dissolved in alcohol, and the weak acid has a conjugate base that has a different color than the unprotonated form. Some go colorless to pink, some go yellow to red. It doesn't always have to be colorless to something else, and it's not always pink, but it will be different colored. Yeah. Oh yeah, yeah. Here, I mean, where is that? It was in 16. What time do we get out of here? 12:25. Ooh, okay. Did you find it? What is it? Six, 6, 4? Oh. Yeah, so what are you looking at? Oh, the thymol blue. Oh, I didn't even know that. So it changes color twice, so it must be polyprotic. Yeah, I think that I never even noticed that. It must then be polyprotic, and that second protonation creates even another species that has a different color. That's cool. I didn't even know that. But that there could be another explanation, but immediately to me that makes sense that it must be polyprotic. Yeah, that's cool. So, yes. Well, no, so it's always an equilibrium, but that equilibrium mixture doesn't always have to have the same relative component. And so at equilibrium, if there's more than this, it's pink, and if it's more, then it's colorless. Okay, and again, it all comes back to Le Chatelier's principle. You guys okay? All right, so guys, moving along then, this is where the rubber hits the road. We now need to talk about titration curves. So guys, you're going to want to put this in your notes. So sort of don't draw yet. I'll sketch it with you. Sort of take in what you're looking at. This is what is called a titration curve. Across the bottom, we've got milliliters, in this case of sodium hydroxide. On the left, we've got pH. Now, guys, before you draw, let's talk about what we're looking at. So, guys, this is a strong acid, strong base titration. So, if you can picture that, we understand that we're going to have a beaker with a stirrer in it, and then we're going to have your burette with the other component in it. So, guys, given this graph, which is starting where? Where does the base start? In the beaker or in the burette? How do you know? Because you're tracking the addition of that. So guys, we know this is the NaOH because we're tracking the addition. How do we know then that the acid is in the beaker? Well guys, the pH meter goes in the beaker. That's what we're tracking the pH of. So how do you know the acid is in the beaker? Because it starts at pH 1, and that's an acid. Do you get the idea? Okay, so guys, with that said, let's scratch this into your notes. So here's what we're going to do, and you're going to want to do this with me. So we'll go black. So guys, we're going to draw the curve. Well, we're going to draw the axes. Then this is going to be pH, and this is going to be milliliters of NaOH. And then these are the important points. You're going to start at pH 1, and then you're going to put pH 7, and then you're going to put pH 14. Then, guys, you're going to put 0 milliliters, 50 milliliters, and 100 milliliters. And then, guys, across the top, you may want to title this Titrating 100 milliliters of 0.1 molar HCl with 0.1 molar NaOH. Okay, so guys, let's talk before we get started. How do I know that this hydrochloric acid is 0.1 molar? How do I know? So don't draw this yet, but let me draw the curve. We'll draw that better in a second. How do I know that this is 0.1 molar HCl? Well, that tells me they're equal. But how do I know that it's 0.1 molar? Go ahead, Anna. No, that tells me they're equal, but it doesn't tell me 0.1. Not if they were both different. So how do I know it's 1 or 0.1 molar? Because it starts at pH 1. Guys, how do you find the pH of a strong acid? This is HCl, right? This is a strong acid. So if the pH is equal to the negative log of hydrogen ion concentration, if the pH is 1, that's the negative log of X, so X is 0.1. But that is also the molarity of the acid, right? Why does that work? Because it's a strong acid. So if I have a 0.1 molar solution of a strong acid other than sulfuric acid, which is polyprotic, then the pH will be 1. So guys, I know that this is a 0.1 molar solution because it starts at pH 1. So then guys, go ahead and draw in the curve. You're going to start at and let me do this more carefully now. Oh, can I not go back? No, it's not going to let me go back. Oh, it's undoing my, here, let me grab a bigger eraser. So guys, as you then draw your curve, here's what you want to do when you do this more carefully. So initially your curve is going to start at 1, and it's going to slope up gently. Then that slope as you near 50 is going to get steeper and steeper until it goes vertical, and then it will tail off in the same fashion that it went in. I pray that your drawing is better than mine, because mine from a distance is horrible. But guys, ideally what you're looking for, of course, is this. So I'm going to use this as my drawing. It is fair. Well, thank you. Some of my best work. So guys, let's now do this. It's important for us to understand the chemistry that we're looking at here. So let's write this down. So sodium hydroxide is in the burette, hydrochloric acid is in the beaker. As these react, our products, of course, are going to be table salt and water. So guys, I'm not quite sure how you're going to write this down because I have a greater degree of freedom than you do because my electronic board allows me to erase liberally. But guys, what I want to do is I want to talk with you about the chemistry that this curve represents. So let's start here and let's talk. So guys, what chemistry is taking place right here where we've got 0 milliliters of NaOH added? What chemistry is going on at this point? There's really, well, sort of. What does it represent? Hydrochloric acid breaking apart into water, right? And if it's helpful for you to draw a very loose drawing of what titration looks like, the idea is the HCl is in here. And guys, this point right here is simply the HCl broken apart into H plus and Cl, respecting the fact that we know that the hydrogen really forms hydronium ion. You okay with that idea? Okay, so guys, understand then that at this point, which we're going to call point number 1, and this is not a, we call this the, let's do this, we call this the initial pH. There is no chemistry taking place other than the acid breaking apart into water. Then guys, let's talk about, and I'm going to try to use different colors. Let's talk, oh, they went blue. So, well, it's all blue. I'll change later. So guys, now let's talk about this region right here. We call this region before, before equivalence. BE. So guys, before equivalence, what is going on inside of this beaker? Well, now we are adding some sodium hydroxide to our acid. And guys, what is that sodium hydroxide doing to the acid? Where on this screen is this chemistry represented? Right here. Guys, this is then the chemistry that is taking place in this region. We are starting with a bucket of hydrochloric acid. And as we add NaOH, this chemistry is taking place. So guys, let's talk about the products. What do we know the pH of these products to be? 7. Why? What do you know about sodium? It's the child of a strong base, so it doesn't affect pH. What do you know about chlorine? It's the child, it's worthless. It also doesn't affect pH. So guys, here's what happens. Before equivalence, the sodium hydroxide is attacking the hydrochloric acid and turning it into both of these things, and those things have a pH of 7. So, as the sodium hydroxide consumes the hydrochloric acid, the products have a pH of 7. So what's going on then is as the hydrochloric acid is being consumed, the pH is going up and up and up and up and up because there's less and less hydrochloric acid that remains because the hydrochloric acid is being converted literally into salt water. As there's less hydrochloric acid remaining in the solution, the pH goes up. Does that make sense? Okay, now guys, turn your attention to this magic spot right there. Label that on your graph. That is called the equivalence point. So again, and we talked about this previously, what does the equivalence point mean? That is the point where you have added equal moles of HCl and NaOH, really NaOH because that's what you're adding. So guys, at the equivalence point, you have added exactly as many moles of NaOH as you started with HCl. That's why we call it the equivalence point. So guys, when we reach the equivalence point, what is inside this beaker? Pure salt water. That's it. We have added exactly as many moles of NaOH as we started with HCl. There is no NaOH or HCl left. It has all been converted into NaCl and water, and we know that Na and Cl are both worthless, bases and acids. They don't attack the water, and that is why the equivalence point is exactly at pH 7. Does that make sense? Because sodium chloride water is pH 7. Yeah. No. Wait. For now, yes. Because if we have think about it. If we have strong. If we have a strong acid and a strong base reacting together, we know their children are worthless. Sorry, that's horrible. We know their children are worthless, and we know it'll be pH 7. So for today, yes, it'll always be at pH 7. But next time, we're going to talk about what if one of these is weak. If it's a weak acid with a strong base, well then one of those children will not be worthless towards water, and that pH will shift. So in strong titrations, rate at 7. In weak strong titrations, it will not be at 7. Does that make sense? Okay, now guys, and so this is region 1, so initial, before equivalence, at equivalence. So now guys, let's switch to this really horrible green color. And guys, let's talk about this. What is happening after equivalence? So guys, at equivalence, we basically got salt water, which may as well be water because the salt doesn't do chemistry. So now as we add more base past equivalence, it's just like dumping base into distilled water. As you add more base past equivalence, it's just like adding base to water. The pH goes up and up and up and up, and it just keeps going up until you run out of base. Do you see it? So guys, this is the idea. The initial pH is a function of the strength of the acid. Before equivalence, the base is consuming the acid and the pH climbs slowly at first. Then as we get close to equivalence and then at equivalence, the pH rises more rapidly, and then we go through pH 7, which is the equivalence point. And then guys, beyond that, it's just like dumping base into water. Yeah?
So can before equivalence be thought of pretty much just like adding acid to water to acid?
No, because you're not just diluting it, you're reacting with it. Yeah, no, it's yeah, and yes, thank you. We just call it after equivalence. You guys okay? Okay. Now guys, let's talk about indicators. I'm going to clean up this mess. So guys, now we need to talk about these indicators. So guys, look at what happens as we are titrating. So as we add base to the acid, we see that the pH goes up slowly. But as we get close to this equivalence point, we get to the point where if we are 1 drop short of equivalence, we're down here at like pH 2. And then we add 1 more drop, and the pH goes from pH 2 all the way up to about pH 10.5 in 1 drop. Guys, that is the experience that you had in lab. You know how it is when you're titrating and you're adding the base and it starts to turn pink, but then the pink goes away, and then you turn it one more time, that one last drop hits that, and boom, it turns really bright pink and it doesn't go back. Guys, that is this experience. But here's the thing that's interesting. Guys, look at phenolphthalein. We use phenolphthalein to tell us when the titration is over. And guys, understand the titration is over at the equivalence point. But guys, phenolphthalein does not change color at pH 7. Phenolphthalein actually finally reaches its pink color at pH 9, and we don't care. Why is it good enough? Exactly. Guys, the same drop that caused the pH to go up to 7 also caused the pH to go up to 11. So it's not like one drop got it to 7 and then another drop got it to 11. That same drop that goes from 2 to 7 goes to 2 to 11 through the point where phenolphthalein changes color. So guys, understand that when you're picking indicators, your indicator does not have to change color at your point of equivalence. It just has to change color on the vertical portion of this line. Just a second. So if you had an indicator that changed color at pH 11, that's obviously not going to work. But so long as the indicator changes color somewhere on this line, it's completely appropriate for the titration. Yeah.
So by color change of the mold, it's going to be like pink all to the right as well, right?
Yes. Yeah. And so.
So it's not just in that.
No. Yeah. So anything. Yeah. And technically, it should curve over with. Yeah. Once it's pink, it stays pink. Yep. You got it. You guys okay with the idea? Go ahead.
Why is that one drop?
I know exactly. Why does that one drop make such a difference? And frankly, it very much is. And there's multiple reasons. Let me give you an easy one now, and we'll talk about the more complete answer when we talk about weak acids and bases. But for now, I think you can be sad. And guys, his question is good, right? I hope a lot of you, why is it that this one drop changes things so radically? And the reason is because pH is a logarithmic scale. So when we're talking about pH, small changes in small changes in concentration are magnified into large changes in pH. So as we get just short of this, we're on the acidic side, and that one last drop consumes all of the acid and takes it to become basic, and that single drop in change is reflected in a huge change in pH because of the nature of a logarithmic scale. You're okay for now. We're going to get into this because there's something else going on, and it has to do with Ka values and products divided by react, and we'll get there next time. That'll explain all of it. That's all you need.
The left was, is that pH? You said concentration of each.
Yes. Good. Yeah. Yeah.
This is just a logarithmic graph.
Yeah. Did you? And that's a great point. That if instead of pH, if this was molarity, it would be linear. No, not molarity, sorry, moles, because then we don't have to deal. So if this was moles of NaOH and if this was moles of HCl, kind of, but it would be linear. So moles are changing linearly, pH is changing logarithmically. And that's what this represents. Okay, so guys, with all of that said, we need to figure out how to tackle this stuff. Holy smokes. We need to figure out how to tackle this stuff mathematically. So we understand initial, before equivalence, at equivalence, and after equivalence. And then guys, a term that you may want to tuck away is the term endpoints. The endpoints are the colors at which these things change, the point at which the indicator changes color, which we now understand is not the same as the equivalence point. Yep. Okay, so guys, now we're going to do some math. We've talked about the concepts behind how this math works, but let me lay out for you the math that we're going to talk about and also the explanations just to reinforce the idea. So guys, we are going to figure out how to calculate the pH in all 4 of these regions. So guys, let's talk. How are we going to figure out the pH initially? Look at the molarity of what? The initial acid, right? In this case, it was 0.1 molar, so it was 1. Now, guys, what about this? How are we going to know the pH at equivalence? It's 7. 4 strong titrations. Next time when we do weak strong, it won't be, but because in a strong titration, both products, the positive and negative ion, are the children of strong acids and bases. They don't mess with water, so the pH will be 7. So guys, these are pretty straightforward. The pH initially is just the negative log of the concentration of the acid, because it's strong. The pH at equivalence is 7. So now all we've got to do is figure out, how do we know this pH and how do we know this pH? So guys, what is causing the pH down here to be low? The answer is there's still some unreacted HCl. Does that make sense? So remember the chemistry. It's HCl plus NaOH forming salt water. So the idea is that down here before equivalence, some of the HCl has been converted into salt water. The HCl that hasn't been converted into salt water is creating a low pH. Does that make sense? Now, above equivalence, why is the pH high? And the answer is because after equivalence, it's just like dumping sodium hydroxide into water, and we've got unreacted NaOH up here that makes the solution basic. So guys, that's what we need to talk about, is how do we calculate this pH and how do we calculate that pH, because this is just the negative log of the concentration of the acid, and this is always 7. Ready to talk about it? Okay, so here we go. We're going to do this by looking at some examples. And so we're going to solve this problem. So guys, it says, and you want to write this down, it says calculate the pH. Calculate the pH when the following quantities of 0.1 molar sodium hydroxide have been added to 50 milliliters of 0.1 molar HCl. You know what I want to do? The correct answer is no. We don't know what you want to do. Let's change these to 100. Because that was, and then this will perfectly follow the graph. Perfect. And then we can understand. So guys, just change 50 to 100 and this will work great. So gang, functionally what we've got then is we've got a scenario where we're looking at the, no, sorry, those should be 50. My bad, change them back. That doesn't work. Here, let's go back and look. These should be 50. And this should be 50. No, and that's the point. That's why I'm saying this, is if we go back here, if we go back to our original graph, guys, it will be 50 milliliters because if we start with 50 milliliters of acid, 50 milliliters of base would neutralize it if they have the same concentration. You see what I'm saying? So it should be there. Okay, so here we go. So let's piece our way through this. So guys, we've got, and so maybe this would be helpful to draw the picture. So we've got our titration set up, we've got our beaker, we've got 50 milliliters of 0.1 molar HCl, and then we've got the 0.1 molar NaOH up here in the burette. So guys, here's the question. What will the pH of this solution be when we have added 49 milliliters of NaOH? So guys, let's contextualize this by putting it on the graph. So if we go back and if we look at this graph by going here, so guys, if we look at our titration curve, realize we're saying 49 milliliters. So we're talking right there, right? So what will the pH be? Well, it's going to be somewhere around 3. But we're going to calculate exactly what it is at 49 milliliters. So let's do that and figure this out. And guys, this is the way this math works. What we're going to do, let me get rid of this mess. Guys, what we've got to do is this. If we've got, right there, okay, if we've got 50 milliliters of acid down here, and if we've added 49 milliliters of base to it, what we've got to figure out is how much HCl hasn't yet been reacted. Because guys, remember the chemistry looks like this. Good night. This day could not get any crazier. So guys, it looks like this. So we've got 50 milliliters of HCl. We've now added 49 milliliters of NaOH. We need to figure out the pH. And to do that, we need to know how much HCl hasn't yet been reacted. But guys, because this is a strong acid-base reaction, what we need to know is how many moles of each we've got. And this is how the math goes. Do this with me. So guys, we started with, and just right along with me, we started with 50 milliliters of HCl. What we need to know is how many moles of HCl are in those 50 milliliters. So what does the math look like? Well, we're going to go 1,000 milliliters is 1 liter, and 1 liter is 0.100 moles. So guys, doing the math, we've got 50 divided by 1,000 and then times 0.1, which is 0.00500 moles. So guys, that's how many moles of HCl we've got in our beaker. Now what we need to figure out is this. How many moles of NaOH have we added to that? So we need to do a similar calculation starting with the milliliters of NaOH. So we're going to go 49.00 milliliters of NaOH. Do the math. 1,000 milliliters is 1 liter. 1 liter is 0.100 moles. And when we do that math, we get 0.000490 moles of NaOH. Did I do that right? 49 divided by 1,000 times 0.1. Oh, is that too many zeros? Oh, it is. I'll do this. Okay, so 0.00490 moles. Okay, so guys, here's what we've said. We've got 0.005 moles of HCl starting out down here. We added 0.0049 moles of NaOH. So guys, here's the question. We started, and I'm going to drop significant digits, with 0.005 moles of this, 0.0049 moles of this have been added. So guys, what did these 0.0049 moles of NaOH do to some of this HCl? Turned it into salt water, right? So guys, 0.049 moles of this HCl aren't there anymore. They've been converted into this. And the pH of that is 0, well, it's 7. So what we need to do to figure out the pH is I didn't even touch it. Guys, what we need to do in order to figure out the pH is figure out how much of this HCl hasn't yet been neutralized. So how can we figure out how much of this hasn't been neutralized? Subtract, and that's why we set it up this way. We do it as a subtraction. So we go 0.005 divide or minus 0.0049, and that leaves us 0.00010 moles of HCl. Now, guys, we can turn that into a pH. How do we do it? Not take the negative log of that. What do we have to do to it first? Turn it into a molarity. So molarity is moles divided by liters. Our moles is 0.00010 moles. What's our volume? 99 milliliters converted to liters is 0.099 liters. Yep, 50 and 49. So 0.0001 divided by 0.099. So I get 0.00101, and that's our molarity. And then, guys, I'm not going to show the calculation, but we can take the inverse log of that, and the pH is 2.99, which, as we saw in the graph, it's about 3. You get the idea? So, guys, let me leave you with this. Guys, imagine, and let me just bring it up on the screen. Well, actually, let me write it down because it'll be in the way. Guys, what if we were at this point? What if we added 51 milliliters of base to the acid? How would the math change? So this would be 51, which would make this number bigger than this number. So all you'd have to do is subtract in the other direction, and the number of moles that you get would not be a number of moles of HCl, it would be a number of moles of NaOH, and then the math works the same from there. You get the idea? Okay, so guys, with that said, let's do this because I know you guys would like to go to lunch. Guys, here's your homework, and let's say this. If any of these problems are KSP problems, don't do them. Well, more specifically, what you'll see is the problems will be in the KSP section. Well, here, I can even look as you're writing them down. So I know that 6 won't be. Won't be KSP. So, and then we're in the 40s. No, the 40s. So KSP, guys, starts at 49. So, yeah, it looks like you won't do 49. You won't do 50. You won't do 50. Yeah, don't do anything past 49. So basically your homework just goes through 44. Guys, have a great weekend. Go to the game on Tuesday. That is all.